Introduction. I guess lots have been in the news about hydrogen. It's clean when you burn it, so the scope 3 emissions are very attractive. However, creating hydrogen can result in GHG emissions, depending on how you do it. So there's a kind of two processes through natural gas. I guess steam methane reforming, where you basically take natural gas and you strip off the hydrogens from the methane molecule, and you end up with what people call gray hydrogen, where you basically create the hydrogen via SMR and release the carbon emissions into the atmosphere, or blue hydrogen, where you basically do the same sort of thing through SMR, but you capture the carbon and it's stored in underground cavern of some sort. And of course, the other process is electrolysis, where you basically take water and strip the hydrogen off the water using a power source of some sort. So green hydrogen, of course, is using the electrolysis process with a non-carbon emitting power source, wind, hydro, solar, nuclear, that type of thing. Electrolysis is you know, 2 to 3 times as much in terms of cost as that is steam methane reforming. Today, most of the hydrogen in the world is created using the SMR process. Lots for refining and other industrial processes is typically what it's used for today. Yeah, I guess some properties, you know, diffusive, low density, which is a issue, and we'll talk about a little later. A lot of flammability there when you compare it to natural gas or oils or NGLs. Transportation, I guess pressurized. You can put in a pipeline, liquefy it, and then of course for transportation techniques, you can use some sort of medium to combine the hydrogen and then release it as you require it. So as everything at in Corey's, we basically when we look at something, we want to take that from the bottom up. What does it mean in terms of cost? Of course, when we see hydrogen in the news lots, it's typically quoted in the dollars per kilogram. And of course, as a gas guy, I always think in MMBTU. So what we've done here is taken the SMR process and charted how that looks at various gas prices to give us a sense of what sort of cost hydrogen production will come in at. Then we can start to think about what this is going to mean for the energy markets in North America. So as this chart shows, natural gas, the gray portion, really is a big component of the SMR process. OPEX, CAPEX changes slightly as we go to higher gas price levels, but really it's the gas input cost that is a big variable here. One of the reasons is, of course, when you take natural gas and try and make the hydrogen from it, you only get about 75% of that natural gas energy being converted to that hydrogen output. So you lose 25% through the fueling and the SMR process to conversion. You see here on the chart at the $3 natural gas price results in $1.15 per kilogram, but 9.35 MMBTU type pricing. So if we think about using hydrogen as a power input. The spark spread for $3 natural gas in a simple cycle, you're looking at a $30 per megawatt type output for that power. And of course, if you're using the hydrogen, you're looking at more like a $93 per megawatt output in terms of the spark spread. So the impact in terms of power cost using hydrogen is significant using the SMR process here. So when we look at potential for renewable natural gas, this chart basically shows the monthly renewable natural gas value. We've taken the renewable fuel standard program, which is an EPA program for the transportation sector. And when you create renewable gas, you get a RIN number, a renewable identification number. So we think about renewable gas for that program. It comes from biofuel, and it's assigned either a D3 or D5 number, and we show those on the chart there. And of course, we do this to give us a sense of what renewable gas is trading at. We've seen deals done for, I guess, a clean natural gas where it's produced in a more sustainable manner. We've seen the Quebec LDC look to purchase some of that from 7gen here or I guess it's now ARC Resources here in Western Canada. We've seen deals across North America on that basis. So this, looking at the RIN value, actual traded numbers, potentially gives us a sense of how much renewable gas or hydrogen as a renewable gas might get you in terms of value. Using that EPA conversion for biogas at 77 BTUs per 1 gallon or 1 RIN identification number equivalent here. And we see on the chart recent trading at for the D5 standard in the 20s, and of course D3s in the 30 to 35, and you know, this run up, of course, as this is required for meeting fuel standards, we can see why this is impacting U.S. fuel prices as well. But at $3 natural gas, that gets you $9 per MMBTU, and if you can trade it in this kind of you know, $15 to $20 range, certainly that makes a lot of sense. So now it becomes how do we get this in the pipeline? So pipeline blending. So if we take some of that renewable gas or hydrogen and call it renewable gas, can we put that in the pipelines that's safe? If we think about growing the hydrogen market, you need access to pipelines, and of course, upfront costs for developing a dedicated hydrogen network would be quite expensive. So if we put a bit of hydrogen in the pipeline, is that feasible? That gives us an economic incentive to convert this SMR blue hydrogen using that CS method to give us access to those renewable gas markets and potentially turning the electrolysis process, if we were able to drive down costs. If we give it a market for hydrogen, potentially you can see more technology and more research into that hydrolysis method to give us a greater hydrogen output for North America. So of course, pipeliners, safety is the most important factor for operators of natural gas pipelines throughout North America. #1 issue. And of course, when we look at studies that have been done, 2013 study concluded that concentrations 5 to 15% hydrogen by volume could be blended and was a viable option. Enbridge Gas in Ontario has received permission from the OEB to blend up to 2% from a electrolysis pilot project in Markham, Ontario, which uses renewable sources on off-peak times to generate hydrogen. One problem is hydrogen is at lower density than natural gas. So you require that kind of 30% more pipeline space to deliver the same BTU content. That goes to tolling issues as well. Do you have to charge 30% more on a BTU basis for hydrogen that goes in your pipe? Do you have the capacity or capability to put hydrogen in and still deliver to downstream markets on a design day of sorts? So those are certainly questions. There's further real world examples in Europe where they're using up to 20% hydrogen in pipeline blending as well. I've just kind of included a couple of North America studies and examples here, but I think there's 3 or 4 in Europe in the 5 to 20% hydrogen blending in pipelines as well. So it can be done. There's a lot of regulatory questions around how you toll that, how much is a perfect amount for the age of your pipe, for the steel you have in the ground, but certainly it can be done safely, which is the number one question. What percentage can your markets receive? And that's a big question, I guess, on the pipeline blending portion of things. So we've also had a look on developing hydrogen export markets. So when we look at hydrogen options to export, you know, the first thing is the hydrogen properties: high energy per weight, however low density. That's really the problem with hydrogen as you compare it to natural gas. Low boiling point. Can be shipped in various ways, pure hydrogen, of course, or you can use it a hydrogen carrier, ammonia, NH3. So you basically attach it to a nitrogen and get hydrogen on the other end of things. And then methylcyclohexane, or MCH, which I'll use for the rest of the presentation. So you basically take hydrogen and attach it to a toluene molecule, and you can transport it then. So the 3 ways: pure hydrogen, similar to natural gas transportation. So when we think about natural gas pipelines, hydrogen pipelines, we think about natural gas, LNG, liquefied natural gas. You can liquefy hydrogen as well, put it on cryogenic tankers, and ship it much like you would LNG. The second option is ammonia, and that's similar to natural gas liquid, so NGL type transportation methods, so trains, and then potentially smaller tankers as well. And then MCH, it's toluene, so basically similar to crude oil transportation, trains, pipelines, potentially, and then large tankers as well. So those are the 3 kind of paths we have for hydrogen exports. So we'll look at some input costs here. We've basically done this case on producing it in Edmonton area, where we have a lot of utilities in terms of the Fort Saskatchewan type area. Create a steam methane reformer there, process it with carbon sequestration. We have the Quest line with a lot of capacity still, so you could easily do this with today's infrastructure in terms of the CCS component of this. And then the hydrogen case, we assume the SMR process, ship it via pipeline to the west coast, kind of almost 1,200 kilometers, and then liquefy it and ship via that cryogenic tanker to Asia. Ammonia, we basically convert it to the SMR CCS into NH3, get some green ammonia, and train LPG train cars, slightly pressurized, and then ship it out to Asia that way. And then MCH, the methylcycline hexane, converted in Edmonton as well, crude type rail cars, tankers, and then send it to Asia that way. And we see here the three pathways, of course, the hydrogen, SMR, uh, LNG plant, and of course, pipeline transportation, and marine to Japan, come in at almost $6 a kilogram, or $50 a MMBTU in terms of when it reaches Asia. So it's quite expensive. Low carbon NH3, we're more at that $4 a kilogram, $32 in Asia. And then the MCH, we come in at just a little under that, a little under 30 as well. MCH, this pathway is certainly reliant on tooling cost in terms of your carrier there. So a few observations when we think about this. If we think about shipping natural gas, LNG, from the West Coast at I guess average AECO prices for the year of a couple dollars, gets us almost $7 input price to Asia via LNG. And of course, you can convert that in Asia for a much more reasonable amount, in terms of instead of that $50 a MMBTU, you're closer to that $9 a MMBTU, which is much more reasonable. SoCalGas has a public utilities approval to deliver 20% renewable gas by 2030 in its franchise area. As we said earlier, traded in that $20 to $33 based on that D3 RINs. So that can certainly be a pathway as well. And then electrolysis here, kind of that 3 times more costly than SMR. But companies such as Plug Power are trying to do mass modular production via, the robotic manufacturing like Tesla to drive down costs. So if you could reduce costs by 50%, certainly you could take that wind solar power off peak and optimize it via the hydrogen and put it in the pipelines and have an opportunity to monetize via this renewable gas requirement from various LDCs across North America. Delivering this hydrogen export, basically we did the 1150 kilometer right of way, based that on the Gateway pipeline that Enbridge had put forth as a proxy to deliver it to Kitimat. NH3, we had rail. It came in at US dollars 9 cents per ton mile. So if we're thinking about doing this from the Marcellus or from the Gulf Coast, that would be a good number for shipping ammonia as well. And of course, the MCH, a little bit more expensive at $10 a ton mile. And in terms of mileage, we're looking at CN line about 1,400 kilometers, and the CP line 1,300 kilometers or so. There's issues shipping things like crude, ammonia, MCH, and so the requirement for minimum liability insurance as well. So in terms of costs, there's a supplementary cost for those dangerous products at about $1.30 per ton of crude oil. Railways also have their own requirements as well, sometimes in addition to this as well. So high cost of insurance could be an issue in shipping things like ammonia and the MCH. Transportation, basically, when we look at West Coast, 21 days from Kitimat to Japan, about the same as Australia. U.S. Gulf, having to go through the Panama Canal, you're looking a 50-day round trip, so more than double that as of Australia and West Coast. We think about the hydrogen content of the various pathways. Liquid hydrogen, of course, 100% hydrogen you ship is delivered. Ammonia, you only get that one hydrogen, or so 18% by volume. And of course, the tooling, you basically add a hydrogen to that and then take that off on the other end. So you really only get 6% of the total shipping weight is hydrogen. So when we look at costs per kilogram per day, you see hydrogen via LNG tanker more expensive. But when we look at the product that you have to deliver on a cost per kilogram of hydrogen per day, you're looking at 14 cents for the MCH, 19 cents for the NH3, the ammonia. So the ability to get that hydrogen to end use markets is a little bit more difficult and a little less efficient on the hydrogen carriers rather than the straight hydrogen as well. So just going through the modeling parameters for a couple of these pathways, of course, we basically did a 50 per day input of natural gas, or sorry, 60 per day input natural gas. We use $3 US for the gas price, and that gets 380 tons of hydrogen per day at a plant capacity. We used a 15% equity return, 7% debt, 35-65 split, and that gave us this 87 cents in terms of cost of hydrogen per kilogram, or about 680 or so in terms of the natural gas or the MMBTU cost per hydrogen. As you see there, CapEx, OpEx, fairly reasonable. The natural gas input is a big driver in terms of costing. CO2 capture, it came in at about $100 a ton, and that gives you about 29 cents in additional costs to get us this blue hydrogen output at the end of the steam methane reforming process. Ammonia, same sort of equity debt provisions. CapEx of just under $1 billion Canadian, or 740 million US. That gave us an end cost of 157 per kilogram hydrogen. The BTU cost over $12 US on that, and a per ton of ammonia cost of about $283 per ton of ammonia. Ammonia has been trading in around the 400 to 700 a ton type cost in terms of North America. So you can see on a ammonia basis, green ammonia is a reasonable cost here. Certainly could stand on its own. Shipping it to Asia, a much more expensive process in terms of using it as an energy source. There's some existing coal plants in Japan. They're looking to mix with ammonia to get a more of a gas emission type burn on the tail end of the plant. So mixing some ammonia, green ammonia, with some coal, and coming out with more of a natural gas type emission in terms of the coal plants. So that's being worked on right now. And of course, time will tell whether that process is economically efficient. And then the MCH, same sort of thing. In terms of plant costs, we're looking at $4 MMBTU in terms of the converting the hydrogen into MCH. So tooling at 57 cents per kilogram, and we're assuming 2.5% losses there as well. So that's a big variable in terms of costing. So if tooling's more like 75 cents a kilogram, it really impacts in the economics, because you're carrying so much of this tooling as well. So you're having to carry the cost of the 6,000 tons of tooling as you attach hydrogen to the tooling to make the MCH. So that's a big variable in terms of the costing of the MCH process. I think it's very difficult to think about using tooling as a hydrogen carrier. It's in my view, it's you don't have alternative markets like you do with natural gas or ammonia. You have a strict pathway, and so it's very difficult to de-risk this process as well. So I guess conclusions. So you have that hydrogen. Everybody loves it because it has clean burning Scope 3 emissions. You have approximately 25% of the energy is lost through the SMM process. That results in natural gas price at $3 into the $10 per MMBTU at a break-even cost at the tail end of the SMR process. You can use blue hydrogen. You can use current natural gas infrastructure and be sold as renewable gas here as well. So that's a positive. You can blend that up to likely safe below that 10%. However, that lower density will reduce the energy delivery capacity of the pipeline. So it's a complementary source of energy, I think, hydrogen in the I guess short to medium term. Exporting hydrogen large distances in commercial quantities is difficult to compete with LNG in the near term. Potentially, if we have that kind of plug and play where they can modularize the hydrolysis process and reduce costs, maybe we can think about that later. But the SMR process is well known and difficult to decrease costs in a big way there. Maybe some efficiencies on the CCS process, but certainly not in the hydrogen process here. I guess this kind of shows you the assumptions we used in terms of average heating value and the BTU per kilogram of hydrogen as well. And then we used a US dollar Canadian exchange rate of 1.3. And I guess with that, we've reached the end of our time period here, half hour in. So with that, I'll thank everybody for their time on today's webinar. And certainly, if you have any questions, you can reach out to me at any time, and we can further discuss this. With that, I'll adjourn today's webinar and thank everybody for their time.